Let's look at another example, and this is a very common situation where we look at a substance cooling. It's actually known as Newton's law of cooling. And it refers to when a hot object is placed into a cooler environment, the rate at which the temperature decreases is proportional to the difference between the temperature of the object and the temperature of the environment. Now, I'm just going to pause it and cough. Hang on. Okay, I'm back now. Let's have a look at this situation in particular. It says, in a kitchen where the temperature is 20 degrees, it's important that we can identify this. Stanley takes a kettle of boiling water. Now, we might not initially realise how important it is to register those words, boiling water, but we will soon, off the stove at time 0 initially. 5 minutes later, the temperature of the water was 70 degrees. We're pretty good at knowing that some information has to be given. But let's put this into perspective based on what we know about the rate of change of a substance when it is proportional to the difference between it and a constant. So I think it's a good idea to recall the theory, for example, and just like in binomial, you really had to be very familiar with an expansion. I would say the same applies here now. I would become really familiar with writing out the general form. Okay, I'm having so many disruptions to this videoing, but never mind, I'm back. Like I was saying, I think it's important that you're able to write down things like dq dt, the rate of change will be equal to k times q minus t. So we write our equations in their general form as we know it, and that from that, then it's possible to get an equation for q, which will be in the form d plus a times e to the kt, where a is our q naught at initially or 0 time minus d, the constant. So if you could write that at the beginning of every question, I think the marker might at least recognise that you've learnt that much about the situation. And then when for this particular situation, you go on to say that what do we know? That in the kitchen where the temperature is 20 degrees, D is equal to 20 degrees. Stanley takes a kettle of boiling water. So obviously this situation is talking about the temperature of the water. It's important to translate that boiling water to the temperature at time 0 is 100 degrees. 5 minutes later, then when T is equal to 5, the temperature was 70. Sorry. Now let's see what we're required to do. It says show that 20 plus 80e to the minus kt satisfies the cooling equation T dt, so the change in temperature with respect to time, is minus K T minus 20, and gives the correct value of 100 degrees at T is equal to 0, and then find K. So I'm just going to note some different features. That our constant is a negative, which probably makes sense, that the temperature will be decreasing exponentially. The rate of change is a negative change. Apart from that, there's not much else to note. Like I said, I'm going to pause the video and write out the solution and then come back and talk about it. So you can see that this equation is behaving like our theory tells us, in that your 80 here comes from T0 minus D, 100 minus 20, giving you 8, and 80, and we know that a solution to this differential equation is in this format. So the temperature is equal to the constant temperature, which is the room temperature, which is the 20. So you can see that this solution is in keeping with our general solution in this situation. So we take that, we differentiate it. We now do this take minus K outside a bracket, introduce 20 and subtract 20. Why do we do that? Because 20 plus 80 e to the minus kt is actually an expression for t, and that then gives us that 20 plus 80 e to the minus k is a solution to this differential equation. It then asks you to establish that T would be 100 degrees when time is 0, and substitute that value in, and that comes out very quickly. Okay, we'll go on and have a look at B, but I'll pause the video and write up the solution and then talk about it. How long will it take for the water temperature? This is another find T. It's probably going to involve some logs. When the temperature drops to 25 degrees. Okay, I'll stop the video, write the solution, and then come back. So you can see that we're finding T when T is 25 degrees, and we'll start with our equation, but the problem is we don't have the value of K. So we're going to use this information from up here to find the value of K. We knew that when the temperature was 70 degrees, the time was 5. So subbing that in, 70 minus 20 is 50, but 50 on 80 is 5 on 8 is the power. K then is equal to log 5 on 8 divided by 5. Don't worry that K is negative. You've got to say that K is negative, but which probably makes more sense to us in this situation, that the rate is changing in a negative direction. And so now we know that to find the time when T is 25, go back and sub 25 and our value for K, and we already had negative for our power, so we end up putting that in, and I leave it in its exact form. Some students want to deal with a decimal, but I find that you need to go to a lot of decimal places, and to me it's just an unnecessary calculator step. So again, subtract 20 and you come to 5, and 5 on 80, but we take the log of that and we'll get the power. Just being careful, multiply both sides by 5, divide by this log, do your calculation carefully, and you'll get 29.4953 blah blah, which you can round to 29.5 minutes. Now, to draw the graph of the temperature time function, you know it's going to be an exponential, and you might check back with the graphs of some of the exponentials back on the first page that I included there for you to help with that. I'll pause the video again. So there you can see that I've drawn a very typical exponential function where the power is a negative, and the key values to note on your axis for time would be 120, and that would be it. So that's all for that example.